Well, good morning here. It's a Saturday morning in Asheville, and we're about to start chapter 5 on lenses. Now, it doesn't take much time for a 300 level course in physics to take something that starts out simple, like the ray diagrams and the lenses, and to get more advanced. So, today we're going to do more algebra, lots of algebra. And please be patient with me. I have injured my finger, and when I write notes, I have trouble. So I'm making more mistakes in this class than I would normally make, but I will show you with an overlay the corrected equation from the book as we go. But I think it's important to do the calculation, always to work things out. It's the best way to learn, I think. I'm a theoretical physicist, and calculation is very important. And you always should study with a pencil in hand in mathematics and theoretical physics and write things out for yourself rather than just look at the book. Now, reading the book is, of course, good for a review, but if you're looking at the calculations for the first time, you really should write them out. So if you have the book open, like when I study in grad school or physics or I do research, I'm working out the calculation for myself to make sure I understand it. So let's look at lenses. They're very much a fun area of physics, and I hope you enjoy the class. Chapter E, lenses. E1, lens types. Now we can look at an analogy here with the mirrors. If we look at a physics principle and optical element, the principle of reflection is realized in mirrors. Light reflects from surfaces, whether they be flat or curved. Now, the principle of refraction is realized in lenses, which is the topic of today's discussion. Now, if we look at the category for a mirror, we had two types, well, three, but let's focus on the ones that are curved. You had the plane mirror, but let's look at the two curved ones. We had convex, that would be this shape, and we had concave, that shape. And now we're going to look at lens. So that's mirror. And now for lens, we're going to have diverging. And that's going to be a cut like this. And converging. Sometimes they call the converging one a convex, but I'd rather stick with the converging and diverging terminology. And let's look at the general idea of the converging lens first. So if the converging lens is very, very thin, then the light would come in and go to a focus, F. You're familiar with this with a magnifying glass and sunlight coming to a focus. The focus where the sun's rays meet. But you don't want to do that though, because that's a very bright spot. It's bright on the eye. And you can also burn something and like cause a fire. If you have the other cut like this, then when the light comes in, very thin lens, it's going to go up, diverge, and the light's going to appear to come from a point on the other side. So some call that a virtual focal point or a virtual focus, since the light doesn't really go there. Now this brings us to a very rare triple word pun. And in a triple word pun, you have each word is a pun. There's 3 of them. And if you look at a perfect one, which I'm going to call perfect pun, there has to be no ofs and thes and in between. So here is the perfect pun. We had a mother and 3 sons. The father had passed away on a ranch, and they divided the ranch into 3 plots for the 3 sons, and they wanted to know what to call the ranch, and they had like a house, or say in the middle there, the dwelling. Now back in the old days, in the vintage TV, they had a situation like that. There was a father and 3 sons, and the show was called Bonanza, and they called the ranch Ponderosa. So what would they call the ranch? And mother said, you should call it Focus, because it's where the sons raise meat. Perfect pun, triple pun. All the words are spelled differently, and they mean different things, and it works. It's where the sons raise meat, and it's where the sons raise meat. Focus. Very, very rare. See if you can think of a 3-word pun during this semester, and let me know toward the end if you come up with one. So now let's look at here a diverging lens in a little more detail. Now, the diverging lens, if you look at this kind of a cut there, at the top, you kind of have something like a prism. Okay, it kind of looks like this at the top. So here, just pull that part off. Then if light ray comes in, and we wanted to like blow this up so we can just study more what's going on, when the light ray comes in, you make yourself a normal. Now your normal is your perpendicular to the interface. So here you have the air, here's the glass. And remember, when you go from air to glass, you bend toward the normal. So you would bend toward the normal like this. And then you make yourself another normal over there. And now when you go from glass to air, you bend away from the normal, which is like that, see? And that's kind of what we did over here. So what we're going to do is use poetic license if the lens is very, very thin, right? And here's poetic license. Poetic license is to let the ray go into the middle and then do 1 bend. But really what you mean is that there's going to be like 2 bends, 1 refraction at the front surface, 1 at the back. But if it's very, very thin, then, very, very thin, we can like get thinner, and sometimes just use a line, just like that's the lens. And you can like maybe do this, all right? And then when you hit there, you're gonna bend up. If you hit there, you're gonna bend down. If you go through the center, well, you go straight through. All right, so that's the situation. Now let's go ahead and label this E2, which is the diverging lens discussion. And let's see if we can look at what happens at the center. Now at the center, it's pretty much flat. So if you pull this center out, you would have pretty much a flat piece of like glass. But what happens if you have that? If you have a thin pane glass, the light goes straight through. I mean, like you look out the window, like nothing weird happens. Now, if we want to blow that up, we would do the same analysis. that the light here would bend toward the normal. But now since these are both flat, this will bend away in like the same kind of amount so that it just shifts a little bit. But if the lens is thin, then this is straight through. So this is looking at ray 2, the one that goes through the center, and this is ray 1, the one that's parallel. And then ray 3 is ray 1 backwards, where if this is coming as if from this F, if you run it backwards and send the light the other way, aim it at F on the other side, it will go out parallel. So like they're the three rules. So we can sketch those rules out in a little bit of a phrase. So ray 1, if you're parallel to optic axis, that would be, your optic axis here. This is the optic axis, go through the center of the optical element. Then that's going to refract. That one refracts as if coming from F. And that's your F. Is if you want, you could say the left F, because when you have a lens, you got if it's a thin lens, you turn it around and get the focal length on either side. And then 2, if you aim to the center, or go to the center, you go straight through. So that passes through. You might want to say in parentheses straight, so it's straight through. And then 3, you're going to aim at F on other side, and then you refract. That's going to refract. I'll say it refracts parallel. All right, so let's look at these 3 again. If you come in parallel, you refract as if coming from the left F. If you run this backwards, that's ray 3, you're going to aim toward F, and well, let's go ahead and give the 3 rules in order. So if you're parallel, you refract as if coming from the F on the left. If you go through the center, you're going to go straight through. So that's ray 1, this is ray 2. And then ray 3, I'll go ahead and give ray 3, you're going to aim at the F on the other side, F and F, and then go out like this. Some books may call that F1, F2, some may call that F prime. I'm just going to call them F. They're going to be the same length. So it's a focal length here, focal length there. And later we'll see with thick lenses that won't be the case, that if you turn the lens around, you get different things happening. Okay, so that's a diverging lens, and if we want to do a problem, the diverging lens array diagram, okay, we have this, and we just go ahead and put an F there, and the same distance here, put an F. And if I have my arrow here, I would go parallel, and then here, as if, coming from there, so to go up, and you could put a little eyeball there that's looking, back down. I like to put the little arrows in the middle of the ray. Then if you come straight through the center like this, and some eyeball down there is looking at it, see where they cross? That's a cute little, you get the small image, and that image there, light doesn't, except for that one ray, and the light really appears to come from there, so that's classified as virtual image. It's on the left side of the lens, and it is smaller, and it is upright, just to give all the characteristics. So this is ray 1, and this is ray 2. Now ray 3 you don't need, we already found the image, we're finished. But if you wanted ray 3, it would aim at the focal point on the other side. And here it does help to have a ruler and do this a little bit better. And then this would go out parallel. And then that would also appear to come from there. So if you use a ruler, be careful. It'll all come out, but just really need 2 rays. So that's ray 3. Aim at the F on the other side and go out parallel. Now, we haven't done any of the math yet. I wanted to show you the power of geometrical optics using the ray diagrams. And here, if you look at all the cases, if you start this out at infinity, this will be real tiny, that F, vanishing, and then as you come in, this will grow up and be the same size when you touch the lens. So it's always good to know all the cases, like you can run all the cases in your mind. So if you're at infinity, the size would be 0, and you'd be at F, at the left F. It'd appear to come from the left F. So just imagine pulling this back, and this little baby here gets smaller and smaller, so like that. Then as you come in, it gets bigger and bigger, it grows up, and then it matches your size and right in front of you up against the lens. Okay, so I think at this point, we're going to go for the converging lens and do the similar analysis with the converging lens. So that's section 3, and then we'll do the math at the end. So section 3, we have the converging lens. And here, if we look at this cut for the converging lens, at the top here, if we just go ahead and break this apart, at the top, that's kind of like a triangle. So that's a prism that's going to look kind of like that, all right? And then if the light ray comes in, and you do your normal, which is your perpendicular to your surface, here you're going to bend toward the normal. We really did this upside down just a second ago. And then here, if you have the normal there, you bend away from the normal. And like we just did that when it was upside down. We did it like we did it here. So just a review. It's like this similar kind of physics. So here it's going to go down instead of going up. And then the poetic license for the thin lens, we're just going to come in here and just at the center shoot down toward here is going to be F, the focal point. And that's a real focal point. That's not a virtual. Light's going to really go there. So you come in down there, it's going to then go there like that. And that's where the sun's rays meet. And that's how you can measure the focal length of a converging lens by having that point there from the sunlight. Just be careful though, because that point is very, very, very bright. Okay, then the center, if you have the center of the lens, here if we just pulled out the center, it would be the same thing. You would have the light that would bend a little bit toward the normal, then away from the normal, and for a thin lens, that's basically going straight through. And then for the third ray, you would run this backwards. So if you come through F, you're going to go out parallel. So let's go ahead and run these rules. Ray 1 is if you go parallel to the optic axis, you're going to refracts through, I like to abbreviate through like that, through F. All right, so that would be the case where if you have your lens here, you got your F and F, both sides like that. So if you're parallel, you would then go through F like that. Like that's ray 1. Then ray 2 is the one that passes through the center. And you can use your own words for this. I mean, this passes through center. All right. Going straight through. It's like having a flat glass. You can't even tell it's there. And at UNCA, once a guy walked through, I think at the registrar or something, walked through the glass and broke it. Didn't know it was there. So when you have the flat glass like this, if it's clean, and our physical plant does a great job, our housekeeping, then you don't even know it's there. It's just it just goes straight through. So that would be the case of going through the center like that. That's the second ray. And then ray three, you're going to, here, this is interesting because you actually pass through F and then go out parallel. So let me go ahead and sketch that for you. If you have, say, F and you have F, if you go through this F, then you go out parallel. Because see, that's ray 1 backwards. If you came in the other way, you go through F. So that's going to be 3. So this says go through F and out parallel. And there are the 3 rules. Let's like do one. Let's like do a case. All right. So if we wanted to do a case before we do the math, and if you do this with graph paper very, very carefully, you get the good answers. You just think of the center here. It's a thin lens. So here's an F and here's an F on both sides, and you say you have some arrow here like this. Then you go parallel, and that would take you through this point here. And then if you go straight through the center like this, you get that. And that's smaller. It's a little bit smaller. In fact, here, probably not very good sketch. But if you went through this F here on this side, the last thing, and then it went out parallel, you see all the 3 eyes would agree where it is. General rule is, with this lens, is that to have the same size, you got to be like with the mirror, twice as far away. And this is a symmetrical argument, beautiful symmetry, that if you go here, you're going to have like this equal to this, equal to that, equal to that, and everything's symmetrical. So it's when you're at 2F away, you're going to be the same size. If you're to the left, you're going to be smaller. And if you're to the right, you're going to be bigger. So if you're like to the right of the double, like say like in here someplace, then when you come in here and go through there, and then go through there, it's like way down there somewhere. So it's good to know. It's good to know the cases. And then when you get to the focal point, see the light's going to go out here like parallel, and like it's like this one off to infinity. But then these 2 infinities meet. Left infinity meets right infinity. And when you get a little bit closer like this, guess what happens? When you've been there and go straight through like this, these eyes think that it came from back here. This is your magnifying glass. See? So this is like with the makeup mirror. When you got real close to the concave mirror, you know how your face got larger. So here, if you have something very, very close, you get this. So like, I like to use magnifying glass because when you get older, it's a little hard to read print. So if this is your print, say in a book, you put the magnifying glass close to it, and then you would look at it on this side, and then you would see the letters that are larger. And that's kind of cool, all right? Power of the magnifying glass. Well, we're ready for some math now. Okay, so for the math discussion, this is E4, and we're going to look at the converging lens formula. Now, for the converging lens formula, it's advisable that I use ruler here, but I'm just going to see if I can pull it off. So here is an F point, and here is a F point. And we'll be over here with the object, and we come in here parallel. All right, then we'll go through F. And then if we come here through the center, like that, we're going to be over here. In the book, you got yourself a real, good drawing, but I like to write everything out because it's like we go slower and we can digest the material better rather than just go reading through the book. So if you look at this, you got your object. This is the height of the object, H-O, and we'll look at your distance, the same kind of terms that we use for like the mirror, S. And here, the f is this focal length, the little f. The capital F's are like they do in math, like a point, and the little f's is like a distance there. So the light's going to go this way, like that, go through there, continue, so that some observers here, like looking, would see that there's a real image there. That's a real image in this case, real, and this is inverted in this case. I always like to do the characteristics, and it's smaller, all right, and it's on the right side of the lens. Right side of lens, like the location. So basically it's saying location, orientation, size, and if it's real or virtual. So if we look at this angle here is theta, then this angle here is theta because the lines cross. And if we look at this one here as phi, then this one here would be phi also. And this is the height of the image. And this distance here is the distance, image distance, from the lens. And that's just to emphasize, that's a converging lens. All right, so let's look at some math here. So the tangent of phi is going to be equal to this height, which is h of the object, divided by f. Okay, so that's one of the results for tangent of phi. But on the other side, look at this phi, which is the same, same angle. The tangent of phi would also be this height, which is the image height, divided by this piece here, which is the SI minus the focal distance, focal length. So this is your equation. So the tangent of phi is the vertical height here, which is HO, and you divide by the run here. This is your F. And then on this side, you have HI over SI minus the F to get this little piece in here. Then for the theta angle, the tangent of this angle would be simply the HO divided by the SO. That's the easier one. And over on this side, the tangent of this theta would be HI over SI. This is very similar to what we did like in the mirror case. Right? And the formula is going to be very similar. It's going to be like the same formula in a sense. Okay, so let's work it out with these two. We basically set this one and this one. What I like to do is get HI over HO from both of these equations. So HI over HO from the left equation would be SI minus F over F. So if you bring the HO down to the right, so you get this ratio, you just got to put this part over to the left, so it's a numerator. And then here, if you want the HI up top and the HO underneath it, you got to bring the SI over to the left top over SO, and like that's like the equation that we want to deal with. So if we, at this point in the game, we are going to solve, to make it look pretty, to make this equation look nice. So let's go and play with it. SO SI minus SOF is SIF. All right. So we brought the SO to the numerator on the left side, and hit each of those terms, SO SI, SOF, and with the minus sign. And we brought that F to the right-hand side and got the SIF. So now what I'm going to do is get the SO SI. I want that on one side of the equation. Let's get the this looks nice to have these together, like on the right-hand side. That looks nice. And then the next step looks like we could pull out the F, would be nice, and have SO plus SI. Then let's try dividing by F. That's kind of nice. Divide by the F. and then we get this. And then we're going to divide by the SOSI, all right, like this, SOSI. And that would give us, starting to look familiar, this would be here, SO over SOSI, and plus SI over SOSI. So here the cancellation of the SOs, we get this, and here we have the cancellation of the SIs, and we always like to write the object one first, and we might go ahead and do it like this. All right, put the SO term first and put the SI one like this. That's a nice form. Very, very nice. Do that, isn't it cool? All right, and that's very similar to what we had done earlier with the mirror. We had the same formula, and some authors might like to do it like this, and you can do it either way you want. That's fine. All right, that's kind of neat. All right, it's the same thing. Very, very nice formula. And notice that with this, SI being positive, it's going to be on the right-hand side. And I like to think of this as space. In other words, with the lens, for the spaces for the lens, the light wants to go through. All right, so that means if the image is on the right-hand side, what's going to be positive image space. Then if the image is on the left-hand side, like the kind we just did with the magnifying glass, that's going to be in negative space. And then for the mirror, the positive space is going to be on image space. It's going to be on the left since the light wants to reflect. And if the image should be behind the mirror, it'll be in negative space. So in other words, SI negative means it's behind the mirror. When SI is negative for the lens, it means it's to the left there. We can just go ahead and do that real fast. For example, if we have, let's say SO is 2 times F. All right, so we're going to do the case which I claim are supposed to be the same height. Then you'd have for 1 over SO plus 1 over SI is 1 over F, your master formula. You'd have 1 over 2F plus 1 over SI is 1 over F. And then 1 over SI would be 1 over F minus and a half, say. So 1 over SI, this would be 1 over 2F, the half, and that means that the SI is 2F, and see, it's positive. It's positive. So this is the case that I was telling you about. That is the very, very beautiful case where you have the symmetry that it has to be nice and symmetric, because see, you have all these are all the same distances. So you come down here like that, and then come through there to there, that this will be equal to this, because this is equal to that, is equal to that, is equal to that. So this is your 2F on the left side and your 2F on the right side. And then if you were to do something like, let's say with the lens, if you were to put it, say, like half F, in other words, SO is F over 2, like, halfway mark. This is going to be, the case that we did earlier, where, if you come through here, you're going to have something, way back here. But let's go ahead and work it out and see. So 1 over F over 2 plus 1 over SI is 1 over F, all right, because this is 1 over SO. So it's just 2 over F plus 1 over SI is 1 over F, and that means 1 over SI is 1 over F minus 2 of those. That's going to be a negative 1 over F. Oh, no, that's, wow, that's weird. That is weird. That's kind of weird. That's going to be at minus F. Okay, we got to draw this one more carefully now and see if this is the case. All right, so we have this, and we have this. And let's say that's the halfway mark. And this is the F over here. So there's the distance away from the lens. And if you put it in the middle, like that, and you come here, now this distance has to be the same on let's see, this big distance has to be the same on this side. So there's your F over here. So if we go through here like that, and then we go through there, that is wild. Look at that. Look at, that's amazing that it's going to be at this point F, like a coincidence, like that's kind of wild. All right, so this is F over 2. So your SO is F over 2, and you're trying to find your SI, just like trust the math. And like the ray diagram, look, it came out that way. It just surprised me at first. I had forgotten that this is a cool thing that does that, but we're just going to check it with the ray. If you use graph paper and all, then you never go wrong. Here it's easy to kind of mess up. You're just doing it with the sketch, like I just said, be careful. But you have the math, then you're in good shape because the math's going to tell you. It's going to nail it. So here you have 1 over, and this is F over 2, and that's going to flip. That's going to be 2 over F, and then you have a subtraction going on. You subtract 2, so you get the minus. That's it. That's what you get, and it works out. See, trust the mathematics. Mathematics always teaches us. Mathematics is very, very good to trust. All right. Okay, and then the magnification formula. That's going to be if you look over here, the magnification. If you take the well, your definition of magnification would be here. This is magnification. So the magnification is the same formula we had before, but we are going to use the minus sign as before because when both of these are positive, that's the case that we did over here. SO is positive, SI is positive, then you get inverted. So that's what the minus sign does. So the same equations. These are the same equations. Just remember that the positive image space is going to be to the right of the lens. This is positive space, and this is negative space for the image, and you're all set. What I would like to do next is the diverging lens formula. Okay, we're doing E5 here, and that's going to be the diverging lens formula. So we're going to look at a diverging lens here. And let's say focal, let's put a focal point here and focal point there. And have some object there. Hit the lens. And this is gonna go up like this. And then one here through the center. Straight through, and there's your cute little image. We're going to call this angle theta, and this angle will be theta because the lines cross. We'll call this angle in here alpha. This is the height of the object. This is the distance the object is from the lens. This is the distance the image is from the lens, and this is the focal length. So we're all set. We're going to then look at the tangent of alpha as this vertical height here. It's thin lens, so the vertical height, HO, and that's going to be divided by F. So that's this triangle in here, where this is the HO divided by F. But the cute little triangle here has, this is HI, the height, HI, divided by this little piece, which is F minus SI. All right, so tangent of alpha is HO over F, or HI over this little piece here, which is F minus SI. And then for the tangent of theta, this is the easy one. It's HI over SI, and it's HO over SO. It's like there's a little triangle, and there's the bigger triangle. So it's HI over SI, HI over SI for the little triangle, and then HO over SO for the big triangle. So these are the equations that we need. So here, if we look at these and play the same game, what is HI over HO? HI over HO, F minus SI over F. Okay, bringing the HO down there and swapping, putting that over on the left. And then here, HI over HO. If you bring the HO down there, you bring the SI up there, you get that. And now we're going to do the same thing we did before. We're going to multiply this out. And this is F SO minus SO SI, SIF, and get the SO on the right-hand side, so it's by itself. So I subtracted the SIF and added the other one. And here, this would be, if we do our division, SO minus SI equals SO SI over F. And then if we divide by the product, like we did before, then we get here, SO is going to cancel 1 over SI, and then here the SI's cancel 1 over SO, so 1 over F. And now I multiply by minus 1, I get 1 over SO minus 1 over SI is minus 1 over F. And here's the beauty, because if I make the SI by convention negative, since it's going to be on the left, then I could write this as a positive, knowing that SI is going to be, now it's going to be negative, because see, the way I set this up originally, SI was positive, but now I'm using convention, and SI being negative, that becomes positive. And if I use the convention after a diverging lens, the focal length is negative, then this becomes the same formula as I had before. Same formula. And the magnification, same idea, because now SI is negative, two negatives cancel, and it's like it's upright. So in other words, same formula. Same formula. All you gotta do is remember that the focal length for a diverging lens is gonna be negative, and the focal length for a converging lens is gonna be positive, and then you use the negative space, image space idea, that if SI is positive, you're gonna be to the right of the lens, and if SI is negative, you're gonna be to the left. So now we're going to go on to do the next section. The next section has to do with two-lens system. All right, so let's look at this. E6, a two-lens system. All right, two-lens system. So we're going to have, and here it does. It does help to use graph paper. I'm not going to do that. And my hand, by the way, has been bad for the last couple of weeks, but we'll make do. All right. So what I'm going to do here is take this focal point for the first lens and make it coincide with the center over here. All right. So that means that in this special case, you know, the focal point is at the second. This makes it easier. It makes this easy to do. And let's say this distance here this distance is going to be the focal length, and it's kind of cool, all right? Because the distance between the lens and separation distance, this is the definition of the focal length. Like, that's what it is. There's a focal length on this side and a focal length on that side. So then if I have an object here, right, where I have my parallel right come in. See, this is going to go then right through the focal point, which happens to be the center of the second lens, so it goes straight through. See, this is why I did this. So I can analyze a simple case, and with the simple case that we analyze, we can learn a lot of physics. Okay, so this height here is the height of the object. And then watch this trick. If I go through F, now when you go through F and you miss the lens, I just make it longer. It's not a big deal. All right, just make the lens longer. Then this is going to go out parallel, but hey, look, parallel for the next lens means just going to go through its focal point. So let's pick a focal point for this lens. Like let's say it's there. So this is F2. So then you have to put F1, and this is F2. Then this is going to shoot up like this, and you get the cute image here. That is wild, all right? But notice that here in this two-step, I mean, I did this ray tracing pretty easily, but I want to do this mathematically. Mathematically, it's going to be a little in 2 steps. We would have to put in some numbers, and what I decided to do to make this even easier, I'm going to put this object at twice this focal length, and I can't do that because I run out of paper. So I'm going to show you a diagram from the notes for the book. So in this case, I have the same situation where I have the focal point of the first lens coinciding with the lens 2, and then that's going to be my focal length separation. But then I put this object twice the focal length on the left-hand side. All right. So when I did that, you get the same idea. You go parallel through the center, and then this one goes through F, goes out parallel, and goes up, and you get that same qualitative idea. But I wanted to show you that there's an intermediate image concept, that if you come down here, and we're going to go out, straight like that, or if you come down, forget that that lens is there, it would have been here. In other words, if you were to sketch this, the image due to the first lens would have been here, all right? And that would have been at, since this is double the distance, this is a special case, it would be then double the focal length. This is double the focal length on this side. That's that case where these are the same height, all right? Same height. But I wanted to show you how to handle this mathematically. So what you do mathematically, and we'll go ahead and let's say, for the sake of discussion, that the focal length is 100 centimeters. So we have some numbers. So that means this is 100 here, and there's 100 there, there's 100 there, and there's 100 here. So I picked this case intentionally because it's like a simple case to analyze the complexity of intermediate image. So I want to find out where this is. I mean, if this is 100, and we'll go ahead and pick this F2, make that F2 to be 50, all right, just to make easy numbers. Then the answer looks like about 33 from just drawing the sketch. And this sketch is drawn accurately. I used a graph paper background on this when I sketched this with a graphics program. So like this is accurate. All right, so then what we're going to do is we're going to use the formula. So the formula over here is 1 over, going to be 1 over 100, because that's going to be 1 over 200, excuse me, 1 over 200, 1 over 200 plus 1 over SI is 1 over 100, and you're going to get the result we got before. You're going to get, it's going to be 200 on the other, it's going to be on the other side, because we know where it is. We know it's 200. Let's go ahead and do the math. So this would be 1 over SI is 1 over 100 minus 1 over 200, all right? And that's like basically saying there's 1 over 100. This is like 1 minus a half. I mean, that's basically what that's saying. So this is 1 over 100 times a half, which is 1 over 200, which means the image distance is 200. Well, we know that because if this is, twice the focal length away, it's going to be twice on the other side. We don't care about that. Lens is not there at this moment. But now, how do we use this information with mathematically? Because this is on the wrong side of the lens. What is this? So here's what you do. Since this is on the wrong side of the lens, what I'm going to do is I'm going to say that this distance, I'm going to say this is the image, become the object for the second lens. So I want to use the formula here for the second lens, and I need to know what I need to put in for SO. Well, since it's on the right side, I'm going to try a negative. Now let's see what happens. I'm going to put a negative 100, and then I have plus 1 over SI. And the focal length of this second lens is 50, because we picked it to be 50, the numbers to be easy to work out. So this means 1 over SI is 1 over 50 plus 1 over 100, okay? I'm going to go ahead and multiply by 50 to get 50 over SI is 1 plus 1/2. That's easier for me to work with. All right, so this is 3/2. So this means the SI is going to be 2/3 of 50. All right, bring the SI on one side of the equation, you get to 2/3 50. And this is 100 over 3, which is 33. And it's positive, which means it's going to be to the right side of the lens. Amazing, like we got it. So I wanted to show you how to handle intermediate image. You just find the image for the first lens, and if it should be to the right of the second lens, use negative sign. You know, if it were on this side, well, there'd be no problem. It'd be like in the middle, and it'd be to the left. And what about the magnification? It looks to me that this thing is about, let's see here, maybe 1/3 of the height or something. So the magnification of this one, well, here's a neat thing. You got magnification. You can always think of magnification as the magnification due to the first lens times the magnification due to the second lens. Now, the magnification due to the first lens, it's essentially going to be a -1. It's upside down, all right? So if we were to use, all right, the formula, I mean, you could use the formula, you know, here. This is minus SI over SO, and for the intermediate image, this was 2F, this is 2F, it's the same, it's the -1. And then for the second case over here, it's minus SI over SO. And what's the SI? Well, the SI, we figured that out to be 33. So this is a 33. But what is the SO? Well, the SO was a -100 because it was on the wrong side, right? So that means -100, like that. And that comes out to be a plus 1/3. And that's because this image did not flip. See, this did not flip. So this is 1/3 of this. Now, if you want the overall effect and you have to multiply the two together, then -1 times 1/3, you know, the total magnification is -1/3. That means this relative to the first one is upside down. So it's beautiful mathematics. I wanted to do you this simple case where you know like where things go because it's easy, but then show how all the math, you know, works out. So just a beautiful situation. So just remember, we find an image due to the first lens, and that becomes the object for the second lens. And if it's on the right side, we use negative sign. We just follow through all the math, and the total magnification is going to be the magnification product of the first lens and the second lens, you know, together. The first one had a -1, and the second one here had a plus 1/3 because it didn't, you know, flip. It's the same orientation. And then when you multiply them both together, you get the -1/3. Beautiful result. Well, we should do one more thing. And this last thing that we're going to do is the lens maker's formula. And we're going to look at the book here because we need a diagram that's fairly carefully drawn. So if we look at this diagram here, we have a piece of glass, and it goes on here, say, forever. And then you have a point A where the ray comes up, and you make a normal, and the normal is from the center of curvature, since the center of curvature, you know, always going to cut the circumference with a 90-degree angle. You bend toward the normal, and you go to point D. So here's the Snell's law is going to be the index of refraction over here is air, so that's going to be air times sine of 1 is going to be then the glass times the sine of theta 2. All right, now let's look at some things here. Put the H in there and put a little epsilon there. And here the distance from the piece of glass to the A is the object distance, and then from the piece of glass, you know, the interface here to the right is the image distance. And so what we want to do first here, and this is a little tricky, law of sines. The way the law of sines works, you might have forgotten this because it's not used maybe as often as other stuff. If you have like alpha, beta, and gamma, alpha, say that's side A, beta has side B, and gamma has side C. Then if you take the sine of an angle, like alpha divided by the opposite, its paired, say, leg of the triangle, the one opposite, that's going to be equal to the sine of beta, and divide by its paired side, which is b. And then the last one is going to be sine of gamma over c. Like, they're all going to be equal. So that's the law of sine. So if we do that, then what we're going to find out here, if we play this game, and let's play it with this triangle, we're going to go with this triangle. Let's see if we go with this one here, like that, and then say we go A, B, C. We're going to go here, and then we're going to go here, like this triangle. Then the sine of phi 1 is you got to go to the side that's opposite, which is this side, and that's r. This is the radius for curvature. And then if we look at, say, the angle in here, we look at this angle is going to be the sine, take the sine of that angle, that's going to be 180 minus theta 1. So 180 minus theta 1 gets you that one. And opposite of this thing is SO plus, see, this is the radius, this is R. So I need SO plus R to get that big one in there. So SO plus R. And now I use a principle from high school. Remember that if you have the sine of supplementary angles, like they're the same. So like if you have like an angle here, say some angle alpha, and then this is the supplement, right? That the sine is going to be, basically going to be this side there, and if you had, the alpha over here and had the big angle there, it's going to still be the same height. You're going to have the same height. So that's something from high school. It's nice to know that the sine of an angle alpha is the sine of 180 minus alpha. All right. So here is alpha, and if I had 180 minus alpha, I'd have this bigger one. But they're the same. They're the same heights. When you have the unit circle, they're the same heights. So like they're the same. So that means we can write down sine of phi 1 over r is the sine of theta 1, all right, over SO plus r. All right, so that's a nice result there. Then this result kicks in, and this result here shows you that the sine of theta 1 over the sine of theta 2. And, in this case, why don't we not make it air? Let's just say that this is, or put NA and NG specifically, then this becomes an NG and an NA, just to keep the index of refraction for now. So then sine of theta 1 divided by sine of theta 2 is going to be NG over NA. All right, so that's another equation. So we got these two equations. And then we need to get one more equation involving, here, let's get one involving the phi, this angle down in here. So if we look at this one, that's a triangle, this triangle here, then the sine of phi 2 divided by its opposite side, r, all right, that's going to be equal to the sine of theta 2 divided by its opposite side. And this opposite side here, what is this thing? Well, this would be the image distance minus r. So that's the image distance minus r. because this is R, and your image distance takes you all the way over to here. So now what I would like to do is write down these three equations for you, copy and have a summary. All right, so the sine of theta 1 over the sine of theta 2 is glass over air, and then the sine of phi 1 over r is the sine of theta 1. Okay, this is what we're just copying down what we had before. And the sine of phi 2 over r is sine of theta si minus r. Okay, so we have these formulas from the analysis, and now we're going to do some math. So if we look at this, let's divide by finding here this middle equation here. Let's take the middle equation and divide the middle equation by the third equation. Okay, so that would mean that the sine here of phi 1 is over the sine of phi 2. All right, so I'm dividing this into the left-hand side. So the r's cancel to get this phi 1 on top, phi 2 on the bottom. And if I do that, then I got to divide this one into this one. All right. There is a 2 there that we lost. Okay, so if we do that, we're going to get here for this one, we're going to get the sine of theta 1 on top, and this is going to be the sine of theta 2 on the bottom, and then this is going to come up top, and then we're going to get this. All right, so let's look at this again. We're going to take this thing and divide it into this left-hand side. So the r's cancel, and you have the phi 1 on top, phi 2 on the bottom with the signs. But to be consistent, we have to take this and divide it into here. That means sine theta 1's on top, sine theta 2's on the bottom, and then this stays on the bottom, and then this, because we're dividing, flips, comes up there. So we get this equation. And then if we use the Snell's law over here, this Snell's law here, it kicks in, this can come in, this Snell's law is going to be in for this one. Then we're going to get here sine, it's the same term here, comes down. And we get here Ng, it's a glass over the air, and then Si minus R over So plus R, like that. Okay, and just take a second to go, let's take a second to go back here. What I would like to do is write down that the tangent of phi 1 is going to be H over SO. So I'm going to write down the tangent of phi 1 is going to be H over SO, right? And the tangent of phi 2 is going to be H over SI. The epsilon, I'm not going to worry about that. So the tangent of theta 2 is H over SI. And that means the tangent of phi 1 over the tangent of phi 2 is going to be, if you take this one and you're going to flip, in other words, you're going to flip this one. So this goes down below, you're going to flip that. It's going to have to be SI over SO. So we're dividing this into there to get the tangents ratio. Then if we divide this into here, we're going to flip the SI to bring it on the top. So we have that equation. Now, we make the famous approximation called Paraxial approximation. And that means that the angles are all going to be small and are going to be close to being parallel. If that's the case, we can use the famous result that the sine of theta is approximately theta and the tangent of theta is approximately theta. So doing that, you know, it's kind of neat to just like not trust this and just to see what's going on. So if you like on your calculator, have some fun with this. And for example, take 10 degrees, and 10 degrees is not really a super small angle. And 10 degrees, you know, times pi over 180 is going to be 0.17 radians. Now this is only true for radians, all right, because you're doing power series expansion of the sines and the tangent. For example, the sine, you know, is like theta minus theta cubed over 3 factorial plus what, theta 5 over 5 factorial. You might remember that from Taylor series expansion in calculus class. And then the cosine of theta is a 1, you know, minus theta squared over 2 factorial. And then there's like a fourth power like this. And often in physics, the cosine of theta is just 1 when you make this small approximation. But see, if you take this and plug this in, watch this, the sine of 0.17 rads is like, it comes out to be a 0.17. It's like, it works. It's working for 10 degrees. And if you push it to go for 20 degrees, where you're looking at the sine of rad 3/4, you know, double the 0.17, this becomes with the sine is 0.35, remarkably close. That's a pretty good approximation. It's like 3% off even for 20 degrees. So that's a pretty good approximation to make. So if we do that approximation, then what we find is that we can replace this equation here that has the ratio of the sines. We can replace this as phi1 over phi2, all right? And then here, we can replace this as the phi1 over phi2, all right? That means I can set this thing equal to that. And that's what I want to do. I want to rewrite this so that we can do that. So let's write that over here. Ng over Na, Si minus R, So plus R is equal to Si, So. All right. Now the rest is going to be just algebra to get a famous result. All right. Algebra. So let's start cranking away. All right. What we do here is we get rid of the denominator. So we're going to want to have Ng Si minus R times So is Na on the other side, Si So plus R. So we basically here bring the denominator to the right side, and we bring the denominator here to the left side. So So here, and then you have the same thing as before. And over on the right side, you have this denominator coming, the Na, and this part, you know, hitting the Si. So this is Ng, and this is a fraction of glass times Si So minus Ng R times So is N air Si So plus air Si R. And next step, let's just go ahead and flip these two to write the SO first. All right, write the SO first. So just a very minor change there. I think for the next step, I like to combine this one with this one. So that's Ng minus Na, So Si, and then bring this on the other side of the equation. So I have here this one with the R plus Ng So with the R. Now I'm going to divide by R and have Ng minus Na. All right, this has a nice result we're going to get a very powerful formula out of here. Na Si plus Ng So over those. And then this gives us Ng minus Na over R is Na over So. This is nice. And Ng over Si. Very, very nice result there. So this result right here, to emphasize that this is dealing with the surface on the first surface, what we're going to do is we're going to write here Na, the air, and I'm just going to put down SO1 because this is the first surface, when we had the glass, the first surface, and we're going to apply this to another surface over here in a second. So let's just emphasize that this is for the left surface, and then that's plus Ng Si1. Okay, so I wrote this right-hand side first over here, and then I have Ng minus Na, and I'm going to divide that by R1, where it's the first surface. So this is the first surface. And then I'm going to play the game that if we go to the next surface, I'll have a similar equation, and the next surface on the right, I'm going to have glass to air. So I'm going to have here glass first, and there's going to be some object for the second distance for the second surface, plus then I'm going to go to air, and that's going to be some image distance for the second surface. And then here I'm going from, I'm switching the order. Instead of going air to glass, I'm going glass to air, so I have to switch these around. Na minus Ng, and I have the second radius. So I have this result. Now comes the part where we have to relate the image of the first surface to the object for the second. And we remember how to do that. We did that before with the intermediate image kind of case, where if you have, say, that image here, and we look at that as an intermediate image, then to compare it to the second surface, we know that this is the separation distance D, and if we subtract the image distance for 1, we will get the object distance for 2. So this is the object distance for 2. This is 2, this is 2, this is 1. So therefore what we're going to do is we're going to replace this object distance with D minus the image distance for 1. That's the trick we're going to do. Now it's more algebra to be done. So let's be patient and continue. What I would like to do is, after I make this substitution, I like to add both of those equations together. So let's do that. Then we're going to have Na over S object distance for the first surface plus the index of refraction of glass, and then the image distance for the first surface, and then we're going to add this other equation. So it's going to be Ng, and then this, I'm going to put this in D minus Si1, that's a substitution. Then we'll have the Na over, we're just copying down, and then we'll have these two terms here, Ng. It's a very, very powerful lens maker's formula we're deriving here. It's going to be nice. All right, plus, and I just copying down. This is just a copy. All right, over R2. Okay, so then the next step is to do a little bit of algebra. So let's go ahead and write down, let's not do too much in one step. Let's just do this, write this down here and write the second term down as is, all right? And write the third term down as is, and write the next term down as is, all right? And then here we'll do the factoring. This is NG minus NA, and this is going to be 1 over R1, and since this is flipped here, this is a minus sign, 1 over R2. See, the lens maker's formula is basically, if you give me the index of refractions and you give me the cuts, I'm going to tell you the focal length. I mean, that's the whole idea. That's like what we're trying to do. Okay, so we come over here. This is NA over S01. Right, plus now I think we're good. We're good to go here. We just continue. And we factor out the NG, 1 over SI1, right? There was a 1 there. And this is going to be plus 1 over D minus SI1, right? Plus lots of algebra. And this is going to be equal to then the same thing that we have over here. Right. Algebra City is what this is. Algebra City. Okay, then if we go to the next step, NA over N object 1 plus NG, we're going to combine these two together. SI1 and the D minus SI2. So this is D minus SI2 plus SI1. So if you look at this first term here would cancel that and it would be the 1 over SI1. And then when you go to the next term, the SI's cancel and you would have the 1 over the D minus SI2 term. A little 2 there. And this is then plus NA over SI2. And this is equal to then the same thing. I like to write this stuff out even though it's the same thing, so I can follow each step and go back later and check my work. So if we look here, this thing is going to simplify because the SI1, now here it got a little bit, we gotta check this. We got a little bit sloppy here. I got a bad hand here. It's almost healed and it's hard for me to write. So if we look at what we have done here, this is a 1 and this is a 1. So this is a 1, right? The 2 is over here. And then this is going to be a 1 and this is a 1. All right, so they're going to subtract off. So this is going to be D over, and all these steps are in the book, by the way. But it's good, always good practice to write things out. All right, and this is the 1. Right, so D minus SI1. All right, like that. I think we have fixed it now. Okay, so let's go ahead and proceed to this next step where we have the NA over the S01, that's this one here, and then plus, I'm going to bring this one down next, this one over here, NA over SI2, all right, that's this one, and then I'm going to go here to the right hand side, subtract all this. So on the right hand side, I'm going to have this from before, right, like that. And I'm going to subtract this, the NG times the D over the SI1, D minus SI1. Okay, that looks good. And then if we go to a thin lens, then that D, which is the thickness, is going to go to 0. We'll handle thickness in another class. So that means this thing is gone. This is good. This is very good. Very nice. N minus 1, 1 over R1, minus 1 over R2. Now, you know, I could have thrown PowerPoints at you and have picture perfect book, but, you know, when I've done that in the past, I have had students tell me they'd rather work it out and, you know, make mistakes as we go, as being human, and fix them, because then you can see all the steps and you can remember them better. And I had a teacher I admired very much in college that would always write on the board everything. Of course, they didn't have PowerPoints in those days, but just writing everything out to just get down to the trenches and to see derivation, I think is best. And it's going to be natural to make mistakes as you go, and then you need to fix them. So that's part of being a physicist, to do that. And then here I'm going to box this off. That's a nice equation. And if you look, this equation here, since this is the very, very first object distance, and this is the very, very last image distance, this is the SO, and this is the SI for the system, So then we can write here then 1 over SO and 1 over SI is N minus 1, like this, and guess what? This is 1 over F for the system. So therefore we have our desired result. 1 over F is given by the index of refraction of the glass and the cuts. See, these are the cuts of the spheres, the circular cuts. So this is the lens maker's formula, which is one of the goals, the last goal for today. I wanted to show you this beautiful formula that, you know, if you have the cuts, okay, so you have here's the cut here, like a radius of curvature in R1, and then you have a cut here at R2, and then you have the index of refraction. Then the lens maker, you know, you use those input parameters, and then you can figure out like the focal length of the lens you're making. So if you're going to make a focal length for like someone to wear glasses, like this is kind of cool. You got your detailed information, beautiful formula, but a lot of algebra to get there, and easy to make mistakes along the way, but that's part of, you know, learning the trade of being a physicist. I'm not picture perfect, you know, I'm not writing down things always correctly, making mistakes all the time. So that's okay, never feel bad about that. We just keep practicing.